Hey everyone, in this video we're going to be talking about spur and helical gears and specifically looking at three Lewis bending equation examples. This video is part of a lecture series on mechanical design too. So we're going to start this section of the video with a first example, which is using US units. And we're told that a steel spur pinion has a pitch of 6 teeth per inch and 22 full depth teeth and 20-degree pressure angle. And the pinion runs at a speed of 1200 RPM and transmits 15 horsepower to a 60-tooth gear. It says if the face width is 2 inches, estimate the bending stress. So using the Lewis bending equation, and for now we've only learned the Lewis bending equation, so we're going to use the Lewis bending, we can start working on this problem. Now the first thing we're going to do in this problem is we're going to kind of write down our knowns in terms of the different symbols that we know. And finally, we're going to draw also a quick diagram to make sure we understand the system. So the quick diagram, I'm going to do a very rough sketch of two gears meshing together, one gear with 22 teeth and one gear with 60 teeth. I'm going to add the T there so that we know its number of teeth. And we know that this is the pinion and the gear. And we know the pinion is the smallest one of the two, and it's the one that runs at a speed of 1200 RPM. Now, the actual direction of spinning doesn't matter in this case, so we're past the point of understanding whether or not in Module 1, for example, we needed to know the rotation. In this case, we don't really need to know it, we just need to know the bending stress happening on the tooth itself. So now what we can do is we can write down some of the knowns from the question. So we can write down that N, or lowercase n, is equal to 1200 RPM. We can write down that capital H is equal to 15 horsepower. Okay, given in the question, that's a power. Then F is equal to 2 inches. We're given that in the question if the face width is 2 inches. And in addition to that, we can also write that the pitch or the diametral pitch is 6 tooth per inch. Okay, and we usually put it 6 T per inch or teeth per inch. We can write it in whichever way we want. And then one more piece of information that we haven't really visited yet is the fact that we have steel as our material. And we'll get back to why we need this in a second. We haven't done this in previous videos in the module, but it'll make sense once we start working on the problem. So now what we're going to do is, since we know we have to find the stress and we know that we're going to use the Lewis bending equation based on this problem, we can say that sigma is equal to kV times WT times capital P divided by F times capital Y. And in the handout that's available with the notes, you'll have in handout 2, you'll have a table giving you the number of teeth with relation to Y. And again, this is also available in your formula sheet for Module 2. So in your Module 2 formula sheet, you also have this available at the very bottom in a different format. But in this handout, we're also going to have these velocity factors. And these velocity factors are for Lewis bending equation. So these are Lewis bending equation factors. And we have factors in US units where velocity is in feet per minute. And we have factors in meters per second. And we'll talk about that in a second. You'll also have all the example problems that we have for this module as well that we're going to be doing throughout this module in this attached handout. So going from there, what we can say is we can go back to our notes and say the first thing we can find is, let's try and find kV. So kV is a velocity factor, and this velocity factor is going to be equal to something. We know that the velocity is going to be in feet per minute. So we're going to use a velocity in feet per minute because we have everything in US units. Now you could use meters per second as well, but it just makes sense to use feet per minute in this case. And we know that if we go back to our handout, we can see that we're going to use this first set of equations, and then we need to figure out, well, which equation should we use? And we're going to use this equation here because we have a steel gear set. And so we see that the first one has cast iron. The other three are all steel. So these are all steel. And what we're going to do is we're going to use the cut or milled profile because it doesn't really tell us any extra information. Hobbed or shaped profile are usually less common, and shaved or ground profile is also less common. Cut or milled is the typical way in which we manufacture gears, so we're going to use that equation. So we're going to use 1200 plus V over 1200 for our velocity factor. So we're going to write that kV is equal to 1200 plus V over 1200. And we know that V is in feet per minute. So now, in order to solve for this equation, we need to find the velocity. And we don't have the velocity, we only have the rotational speed of the pinion. Since we know the rotational speed of the pinion, we can translate that and say velocity is equal to pi dn over 12. And if we go to our formula sheet for module 2, if we actually look, for module 1, so if we go to our module 1 formula sheet, we'll see that we can find some of these equations. We can find that V is equal to pi dn over 12 whenever we have US units. This is also part of our notes of module 1, so we have that available right here if we need to have access to it. Okay, so going back to our notes, we have pi dn over 12, then that means we're going to use our velocity or our pitch line velocity for our pinion, but again, that would be the same pitch line velocity as our gear in the system because they're touching, so they're going at the same speed or the same velocity. So we can write that d2 is equal to n over p just by rearranging the diametral pitch equation, which would be equal to 22 teeth divided by 6 teeth per inch. And we would get that diameter 2 is equal to 3.667 inches. Okay, now following that, we can then say that velocity is equal to pi. And remember that the 12 takes care of the units for us from converting inches to feet. So we have 3.667 times 1200 divided by 12, and that gives us 1,152 feet per minute for our velocity. So now we can find our velocity profile, our velocity term, which is our velocity constant, or kV, is going to be equal to 1200 plus 1152 over 1200. And we're going to get a kV of 1.96. So we can see that if this was a static problem, we would have a kV of 1, and we can see that the velocity actually has an effect of essentially doubling the actual bending stress felt by the gear. So the change in stress is actually quite significant because of the velocity. So the velocity is not just a term that the kV is not just a term that we can get rid of. Okay, so going back to our initial problem and our initial equation, we can now check off that we have our kV. Now we also have our capital P, we also have our F, so we're going to take care of those. We're going to put check marks around those. And the next term we need to find is WT. So in order to find WT, we're going to write the equation for WT, and we're going to write the equation for WT for US units, which is 33,000 H over V. And if we write this down, we have 33,000 times 15, which is already, the units are already taken care of, over 1152. And we get that WT is equal to 429.7 pound force. Okay, so those are the amount of pound force, or the tangential force coming out of the gear tooth. okay, or the tangential force essentially that the gear tooth feels because we have that reactionary force between gear 2 and gear 3. So now we can say that we have Wt, we have that value, so we're good to go. The last value that we need to find is y. So y, we know that the pinion has 22 teeth, and we're asked to find the stress on the pinion itself. So going back to the question, we're said to estimate the bending stress. So we could estimate the bending stress on the pinion or on the gear. That would give you a slightly different y for each one. So in this case, we're going to estimate that it's on the pinion, and we're going to say y of 22. We usually write it y as a function, or we just say y of 22. And then we go look up in our table, either the handout 2 table or the table in module 2 formula sheet. We go to 22 teeth and we see that we have 0.331. So going back to our notes, we can see that we have 0.331. And then based on that, we can find our sigma because we have all the information available. So we have that this is 1.96 times 429.7 times 6. All the units work out to where the sigma is in PSI. So divided by 2 times 0.331. And we get that this is equal to 7,633 PSI. So that solves our first problem of this set of problems that we're going to solve. So now we're going to solve another problem from our handout. I'm going to copy it over. I have it here on the right side, so let me just copy it over. And this one's going to be in SI units, so it's going to be a slightly different process, but very similar idea. So we have a steel spur pinion has a module of 1.25 millimeters, 18 teeth cut on the 20-degree full depth system, and a face width of 12 millimeters at a speed of 1800 RPM. This pinion is expected to carry a load of 0.5 kilowatts. Determine the bending stress. So one thing that's important here is what I would do here is I would pause the video and try and solve this problem by yourself if you can. You can even try and do it with a classmate if possible, or with someone else and try and figure it out. But if not, you can follow along, but I would highly suggest to try and solve this problem by yourself because you've already seen the process in the previous problem, and it's exactly the same process, just with different units. So I'm going to write the units out first, just so that we know the units for SI problems. The units are going to be, and I'll put them in little square brackets so we know that we're talking about units. So sigma is going to be in megapascals. WT should be written in newtons. F, or face width, should be written in millimeters in order to get that megapascals. And M, or your module, should also be written in millimeters. Okay, and the equation for SI units is slightly different. We have sigma is equal to kV times WT over F times module times Y. And again, the module is at the bottom now because it's the inverse of K, and they're slightly different units. So based on the problem, I'll leave the problem on the top here. We have that F is equal to 12 millimeters. We have that M, or the module, is equal to 1.25 millimeters. And we know that Y of 18, if we go to the table, I'm not going to go to the table, but you can go in your own time, is equal to 0.309. Okay, and I'm going to go a little bit faster through this problem just because of the fact that we've already done this type of problem already, so we can kind of work a little bit faster through it. But there are a few things that we want to talk about. So first things first is we need to find KV just like before. So KV is going to be, we have to find KV, and we're told that we have a steel spur pinion again. So we're going to go to our handout, and we're going to go to the second KV with the velocity in meters per second because we want to find the velocity in meters per second. Another way to do it would be to find KV in feet per minute and then convert it to meters per second if you want to, but it's just easier to go directly to that second set of equations. So we're going to use KV is equal to 6.1 plus V over 6.1 because we have a cut or milled profile for steel. It doesn't tell us any specific cutting mechanism other than a standard steel gear, and we're going to go with this material. So we're going to go with this. We're going to go back to our notes, and we're going to write 6.1 plus V divided by 6.1. Okay, and now what we need to do is we need to find V. Now, in order to find V in SI units, it's a little bit more complicated because in our formula sheet, we haven't written down an actual conversion between SI units and velocity with RPM. So we've only written that we have V is equal to omega R. Okay, and this is from our formula sheet from module 1. And omega R can be, so we have, is usually omega is in radians. So we need to convert this and write that we actually want to write it in terms of RPM essentially. Okay, so to write it in terms of RPM, what we need to do is we need to write 2 pi times n divided by 60. And n is in RPM. The 60 converts our RPM to radians, revolutions per second, and then the 2 pi converts it to radians. So that's how we get our conversion between omega as a value in radians per second versus 2 pi n over 60 would give us our value in our conversion between radians per second and RPM. So we can work with that directly. Since we have the RPM, we're going to use the second part of this equation. Now, moving further, we can say that we can write 2 pi n over 60, and then we can say that it's multiplied by d over 2. Okay, we have radius is diameter over 2, and that simplifies our equation because we can cancel the 2's, and we're left with an equation that says it's equal to pi dn over 60. So if you ever have to use this in an exam or you want to use this to solve problems, you can add this to a formula sheet where you can say that for SI units, V is equal to pi dn over 60 if n is an RPM, which we've defined for this class as RPM. So now we can plug in our different equations, our different values for the equation. So we have pi times diameter. So diameter, we're going to find really quick through module times n, which is going to be equal to 22.5 millimeters. So it's number of teeth times the module, so 1.25 times the number of teeth. We get 22.5, and so we're going to plug this in, 22.5 millimeters multiplied by 1800, all divided by 60, and we get, and you have to be careful with units once again here, we have millimeters times RPM, so we get 2,122 millimeters per second. Okay, remember that we're actually calculating this in per second because we have the divided by 60, and then we can convert that to 2.122 meters per second. Okay, so it's up to you if you want to write the diameter in meters or in millimeters. If you write it in millimeters, you get millimeters per second. So slightly more difficult to find the pitch line velocity for SI units, but it's just a matter of understanding the equation directly. Okay, then we can finally solve for kV. So kV is equal to 6.1 plus 2.122 over 6.1, and we get that kV is 1.348. So still a significant 35% increase over a static problem, but not as significant as the first example. Then we need to find WT for our equation. So same process as before. Now we're going to use 60,000 times H over pi dn. Okay, the reason we're using this equation is because we have SI units now, and we're going to write 60,000 multiplied by 0.5 given in the question, divided by pi, and remember all the units are taken care of here already, 22.5 times 1800, and we get that that's equal to 0.2358 kilonewtons. And finally, if you actually plug in all your values to the final equation, we have F, we have M, we have Y. we can find our sigma, and you can do this in your own time if you want to, but the sigma you would get would be 68.6 megapascals. Okay, so that concludes the second problem that we're doing. Now, we want to do a third problem to try and understand a very specific thing that might be counterintuitive at least. Okay, so let's do a third problem that is slightly different in format, but uses the same theory. So I'm going to copy it over, just as before. Okay, so this next problem tells us a 20-degree full depth steel spur pinion has 20 teeth and a module of 2 millimeters and is to transmit 0.5 kilowatts at a speed of 200 RPM. Find an appropriate face width if the bending stress is not to exceed 75 megapascals. So in this case, what we're told to do is actually we're flipping the problem, right? We're trying to find an appropriate face width if the bending stress is not to exceed 75 megapascals. So remember that, so we're going to write the equation down. We're going to say sigma is equal to kV times Wt over Fmy, okay? And of course, we're told to find an appropriate face width. So what we do is we say, well, if we need to find the face width, we can rearrange this equation and we can say that F is equal to kV times Wt divided by sigma my. Now, we're rearranging this equation in order to find a face width, okay? One thing that's important to understand in this question, in this example, and we'll definitely discuss this as we are going through the problem, is that sigma is a result of other decisions. So all the terms on the right side are pretty much decisions that we make. And the term on the left side is a result made from other decisions. So we can't just say like, I want to apply a stress of 75 megapascals. No, the stress is a resultant of all the other decisions, okay? So we always need to think of that as our way of figuring out the resultant, and we always need to think about that when we're doing these types of problems, when we're rearranging our equation. And we'll see why, okay? So let's try and solve this problem for F based on the fact that sigma should be, so we're told sigma should be less than or equal to 75 megapascals. Okay, it shouldn't exceed 75 megapascals. So what we can do is we can look for the worst case scenario, which would be 75 megapascals. Okay, we're going to assume that we're going to do the problem for the worst case scenario up till the limit to figure out what face width we would need in order to figure out what 75 megapascals would give us. Now, the other terms given in the problem, we have H is equal to 0.5 kilowatts, and N is equal to 200 RPM, okay? And based on that, we can then solve for a few different things. So we can solve for, and I'll go a little bit faster for this problem because we already know kind of how to solve all the different parts of the problem. So Wt would give us 1.194 kilonewtons. And then kV, we could solve from 6.1 plus V over 6.1 because we have SI units. We know that diameter would be Mn, which would be equal to 40 millimeters. And therefore, we would have a velocity calculated from pi dn over 60, which would give us, if we actually work through the math, 0.419 meters per second. Okay, so we have that term right there. Our kV would then be equal to 1.069, and our y for 20 teeth this time would be equal to 0.322 based on our table in our handout or in our table in our Module 2 formula sheet. So we have all the terms. So now what we want to do is we want to write what the face width would be. So we can say face width is equal to the different terms. So we have kV times WT, so 1.069 multiplied by 1,194. And remember, this has to be in newtons. We have to be careful with that, okay? That's something that we have to be careful for. The units are in newtons, not kilonewtons. And then we divide by 75, which is our sigma, multiplied by 2, which is our module, multiplied by 0.322. Okay, and if we solve for the face width, we get a face width of 26.4 millimeters. Okay, so all is good, and we know that we need a face width of 26.4 in order to solve our problem. Now, thinking about this a little bit, okay, if you think about this a little bit and you found that when you have a sigma of 75 megapascals, you get a face width of 26.4, okay? Now, if you were to redo this problem, and this is where the discussion comes a little bit into play, if you were to redo this problem and you said, well, I'm going to do this problem and I'm going to think about it, well, should face width be 26.4, or should it be at least 26.4, or should it be greater than 26.4 or not? So let's assume that we solved the problem and we said, well, the face width is equal to 26.4. So if I were to plug it back in so I'm going to write down the equation for stress again, saying it's equal to kV WT over F my. If in this equation I plug in a face width of 26.4 millimeters, I would get a result of sigma is equal to 75 megapascals. Okay, that makes sense because we just found that F is 26.4. Now, if I plug in a value of 30 millimeters, so let's say instead of putting, and I'll draw it in blue this time, so let's say I put 30 millimeters, what would happen to our sigma? Our sigma would be less than 75 megapascals. So that means that if I increase my face width over 26.4, then I would never exceed 75 megapascals. Okay, so increasing my face width obviously makes sense in terms of what I need to do if I need to not exceed 75. So if I write in red here, I can say that F should be greater than or equal to 26.4 millimeters. And we've proven that that's the case based on this box of information. So I'll highlight this box of information just so that we know that this is proof that it works. And this is our final answer shows that we get that F should be greater than or equal to 26.4. Now, sometimes what happens is people could get confused and people could get induced in error by saying, well, if I'm looking for a face width and I'm going to plug it back into this equation instead. So some people would say, well, let me try for sigma of 80 megapascals, what happens? Okay, and if you look at sigma of 80 megapascals, what would happen? If you say face width is equal to all of this divided by 80 megapascals, we see that we actually would get a lower face width, okay? And this is an incorrect methodology. So you can't use to check your answer, you can't just modify your sigma value in green, Okay, I'll put it in green here. You can't just modify your sigma value in green and say, well, now my face width is lower, so it works for a lower face width. Okay, because sigma is a resultant of all the other decisions that you made. It's not a design parameter, so we can't just change our sigma. So we always want to test if our face width is correct, and if our face width, like which direction we need to go with our face width. It kind of makes sense that a wider face width would work better for to withstand more stress. Okay, and obviously it makes sense that we should use this equation as our tester. Okay, now if we use the face width equation, the one that's highlighted at the top here, what would happen is if we plug in a value of 80, for example, and we said, well, 80 megapascals, now we have a face width that's lower than 26.4. Does that make sense why that is the case? Okay, so try to think about that and try to see if it makes sense for you. And now I'm going to explain why it would be the case. So if we think about it, if we have a face width that is lower, okay, and we get a resultant force, a resultant sigma that is higher, like 80, it means that essentially our face width is not enough to maintain 75. Okay, so we always want to revert it back to the original equation, because 80 is not a decision, it's more a resultant of what's happening. So it makes sense that if you make your face width smaller, let's say you make your face width 20, then you might get 85 or 90 or 95 as your stress, because it won't be able to take enough stress with the width. Okay, so hopefully that made sense. And if there are any questions on this, you can definitely let me know in the comment section, or by message as well, so that makes complete sense to you. Okay, so this concludes the bending examples. In the next video, what we're going to be doing is we're going to be looking at surface durability and doing some examples on how we can figure out surface durability of our gear teeth in a way that is more simplistic than once we get into the AGMA method, which we'll get into after that. So we'll see you in the next video.